Welcome to Further Solutions Academy once again, and I hope you're enjoying our videos, and I hope you have been following up on us. So this is Further Solutions Academy once again. Please do well to share our videos and subscribe to our YouTube page. And if you want to reach us for any contributions or any information at all, please this is a mobile number at which you can reach us: +23480 344 You can chat us on WhatsApp, you can chat us on Telegram, whichever one you're okay by, and you can even give us a call if you have anything to reach out to us for. So today we will be discussing a popular trend in chemistry that is known as periodicity. Periodicity of elements. Periodicity of elements. So as you can see across the board, we have a small picture of the periodic table, which we'll be using for today. Not too legible, but I think we can still make do with it. I believe we can still make do with it. So let's get to it. When we talk about periodicity of element, before we go there, it is expedient that you realize that when we are talking about the periodic table, it's actually bigger than it is, because there are quite a lot of information contained in the periodic table. The periodic table is the table that contains the elements arranged in their increasing atomic mass number, and the whole periodic table has been designed by Mendeleev, and it has been revised where we have the modern periodic table. And on the periodic table, there are specific alignments that we need to take note of, and one of those things are called groups and periods. So we have the groups, and the groups are the vertical ones, while the period are the horizontal. Ones. So if we look at the periodic table, or you have a sample of a periodic table, which I would suggest that you use for this lecture. So we have the groups from the vertical ones, which is hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So across the period, we have hydrogen and helium on period 1. We have lithium, beryllium, boron, carbon on period 2. So these trends, there are some specific characteristics that are pertaining or that are reoccurring in these trends, either down the group or across the period, and those specific characteristics are what we call the periodicity of these elements, and what we call the periodicity of this element. Please do well to follow me. So we'll be discussing the periodicity basically under 4 different areas. First, we will be starting with the atomic radius. We also have the ionization energy. Ionization energy. We also have the electron affinity. And lastly, we have the electronegativity. Now, one way or the other, these 4 characteristics have a way of influencing the properties of this element. So as you follow me through this lecture, we will be exploring the 4 of them. But let's start with the atomic radius. Definitely, chemistry is under science, and science involves mathematics. And mathematics, we know, we have heard the word radius before. So when we talk of radius, we are talking about something that has to do with the circle, right? And we say a radius is the point from the center of the circle to the circumference of the circle. From the center of the circle to the circumference of the circle. So if that is what we are talking about, alright, so like I was saying, I said we have the circle, and from our mathematics, we said radius is the point from the center of the circle to the circumference of the circle. So if we're talking about an atom, although you know just from the different structures of an atom that an atom is something of this sort, although not definitely, but something of this sort. So when we say an atomic radius, we are referring to the point from the nucleus of an atom to the external electron on an atom. From the nucleus of the atom, to the external electron, to the electron on the outermost shell of that atom. So that's what we are talking about when we are talking of atomic radius. And the atomic radius, if we look at it, starting with down the group, we will look at hydrogen, lithium, sodium. We realize that lithium has a bigger size than hydrogen. Lithium has a bigger size than hydrogen. Sodium has a bigger size than nitrogen. Okay, let me write this out so you can see it. Sodium has the biggest among these three, and this is down the group. So what can we say? Atomic radius increases down the group, but across the period we find out that it is not the same. Because why? Let's use period 2 for example, where we have lithium, we have beryllium, we have boron, we have carbon. So across the period it is realized that this is smaller than this is smaller than this is smaller than this. How? Because of what we call nuclear charge. Because of what is known as nuclear charge. Excuse me, please. So when we say the nuclear charge, what is responsible for this? If you agree with me, when we are talking about down the group, when we have hydrogen with an electronic configuration of just 1, so we have just 1 electron on the outermost shell, right? When we go to lithium, that is 2 and 1. So we have the first shell and we have one other shell. When we go to sodium, permit me to draw that of sodium here. So, okay. When we go to sodium, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, if you see the graduation in the sizes, you realize that as you move down the group, more shells are added, even though they all have 1 electron in their outermost shell. More shells are added. As the result of addition of more shells, it is realized that the atom increases in size. So the size increases from the center to the circumference. Because why? More shells are added. If we go to potassium has 4 shells, which is way bigger than sodium. So that is how the graduation is. But across the period, we realize that it is not like that. We don't have something of sorts. Across the period, let's say we are using lithium, beryllium, and boron. Lithium has an atomic number of 3 rather. So we have 1, 2, 3. Beryllium has an atomic number of 4, 2, 2. Then that means we have 1, 2, 3, 4. Boron has an atomic number of 5, 2, 3. So we have 1, 2, 3, 4, 5. If you realize they all have the same number of shells, but something is changing, which is the addition of an electron on each of them. So this has 2 shells, this has 2 shells, and this also has 2 shells. But electrons are being added on the outermost shell. And because of the result of this electron being added, there is an effective nuclear pull from the nucleus. There is an effective nuclear pull on the nucleus. Because why? The proton number and the electron number, there is a pull between the proton and the electron on the outermost shell. And this pull is discovered to increase as a result of additional electrons added to the outermost shell. So as it continues to, as it's being added, there is a shrinking that brings the electrons on the outermost shell closer to the nucleus, thereby making it smaller. So the more electrons I had on the outermost shell, the shrinker it becomes, the smaller it becomes, and that is how the atomic radius reduces or decreases across the period. If you check the sizes of the atomic radius, you realize that this fact holds, and it is very, very proved from what we have said so far. So let's go to the next one. But before we go there, let me call your attention to something. Atomic radius for a cation, which is a positively charged atom, for instance, sodium ion has a smaller atomic radius than sodium. Why? Because sodium ion has lost 1 electron. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. But here we just have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One electron is lost, and because that electron is lost, there is the loss of one shell already. So it is discovered that this has a smaller atomic radius than the corresponding atom. But for a cation, for an anion rather, for instance, let's say we are talking about something of the chlorine atom, or any cation, or any anion rather, any anion, the atomic radius is noticed to be bigger. The atomic radius of the anion is noticed to be actually bigger than the corresponding atom. It's actually noticed to be bigger than the corresponding atom as a result of a greater repulsion that comes when an electron is coming to the to that particular shell, and the presence of other electron, negative. So there is a greater repulsion, and this causes it to have an increasing size for anion or negatively charged atom than their corresponding atoms. Next, we'll be going to the second one, which is the ionization energy. We'll be going into the ionization energy. We are behind time, and I just okay. Now, on the ionization energy, first you need to understand what ionization energy means. Ionization energy is the energy required to remove a loosely bound electron from an isolated gaseous atom. So if we have an atom like sodium, which has one electron on its outermost shell, and you want to remove that electron, the energy required for you to pull out the electron is referred to as ionization energy. Let's say we have an equation of something of this sort. All right. So this energy required is known as ionization energy. And it is influenced by three different things. Number one is the size of the atom. Then also the charge on the nucleus can also affect it. And lastly, another thing that can affect it is the screening effect. The screening effect can also affect ionization energy. But one thing you should note on the ionization energy concerning the trend is ionization energy increases across the period and decreases down the group. Increases across the period and decreases down the group. So how do we explain this phenomenon? Let's get to that. Concerning the explanation. So like I said, how do we explain this phenomenon? Looking at the concept, the energy required to remove a loosely bound electron. If we look at down the group, please realize that down the group you have similar number of valence electrons on the outermost shell. Okay, valence, outermost, okay, same thing. Sorry for that tautology. So on the valence shell, we have similar number of electrons down the group. Lithium has just one, is in group 1. Sodium has just one, is in group 1. Potassium has just one, is in group 1. Rubidium 1, and like that. So for the group 2, they all have two electrons on the outermost shell, and so on and so forth. So if we're talking about the energy required to remove a loosely bound electron in the down the group, because they all have the same number of electrons, so similar energy is required to remove that one electron from the outermost shell. Nevertheless, remember we said it is influenced by the size of the atom. Please note that it is very difficult to remove an electron from a small atom. So the smaller the size, the harder it is to remove an electron. The smaller the size, the harder it is to remove an electron. So what we are saying is what we are saying is down the group, so down the group, it becomes easier for you to remove an electron from the outermost shell. Reason being the fact that the size is being increased. The size is being increased. So at a point in time, it becomes the effective nuclear charge is reduced and it is lost at a point in time. For instance, let's say we have for lithium, whose size is like this. For sodium, the size is like this. So it is easy for you to remove an electron from sodium very quickly than for you to remove from lithium. Because why? It has a bigger size. So as the size increases, the ease at which you remove an electron also the energy that you use to remove the electron also reduces. The energy also reduces. Remember, we said the energy required to remove. So you don't have to spend so much energy to remove an electron because the ease is just there because it is big. So it is very easy to just remove it since it has a very large size. And coming to across the period, it is not that way. Why? Reason being the fact that across the period, we realize that because they all have smaller sizes. And also, one thing that affects the element across the period is because the additional electrons are being added. So because additional electrons are being added, there is a graduation of increase in electron across the period. And this makes it difficult. You will need more energy to remove, let's start with lithium. Lithium has just one electron on the outermost shell. It is easy for you to remove just that one electron, even if the size is small. But the energy you use to remove an electron from lithium is not the same you will need for beryllium. Reason being the fact that what? Beryllium has a very has a smaller size than lithium. So, and it has 2 electrons. So for you to remove just one electron, and let me remind you of something in physics. I'm just saying this as a reference. In physics, there's something known as Heisenberg uncertainty principle. And Heisenberg uncertainty principle states that it is impossible to know the momentum and the position of an electron of an atom at the same time. And obviously, you know that in the structure of your atom, the electrons are moving from place to place. The electrons are moving from place to place. The electrons are moving from place to place. So it is impossible to detect the position. So the energy required to remove just one, if you knew it was just one that was moving within this orbit, is easy. But when there are now many, it becomes so difficult to just pull out one electron. And that is why the ionization energy increases across the period. But nevertheless, there are some discrepancies that you should note. Some discrepancies in the area of the ionization energy, and one of those discrepancies occurs between beryllium and boron. Beryllium atomic number 4 with the electronic configuration 1s2 2s2, then boron atomic number 5 with the electronic configuration 1s2 2s2 2p1. This is discovered to have 900 joules per mole, and this is discovered to have 799 joules per mole. Now, how come, if we are saying ionization energy to increase across the period, what is wrong with this? Something is wrong. This discrepancy is as a result of beryllium having a closed shell. The valence shell of beryllium is a closed shell, making it act as an inert atom. So it becomes very, very difficult for you to pull out an electron. It becomes very difficult to remove an electron from beryllium than it is in boron, because boron just has one electron in the p orbital and is quite unstable. So the ease at which this gives out electron is much better than that which we give. The same thing happens in nitrogen and oxygen. Nitrogen has a partially filled p orbital. Oxygen is quite unstable to an extent. So it is easy for you to remove from oxygen than to remove from nitrogen. Nitrogen has an ionization energy of about 1,400 joule per mole, and oxygen about 1,310 joule per mole, which makes it lesser. And those are the major discrepancies. We may have others, but for this class we just talked about those ones, so for you to understand. The next thing we'll be going to is the area of the electron affinity. The electron affinity. Now, electron affinity is similar to that of ionization energy. But what is electron affinity? Electron affinity is the energy released. The energy released from when an electron is added to a neutral gaseous atom. The energy released when an electron is added to a neutral gaseous atom. And we have this kind of equation. Let's just say plus E as this. What does this mean? This means that this is an exothermic reaction. Because why? Energy is released. Energy is released into the surrounding. So there is an exothermic reaction, and that is electron affinity. The trend for electron affinity is that across the period, electron affinity increases, but down the group it decreases. Across the period, it is discovered to increase, but down the group it is discovered to decrease. And one of the reasons why we have this is as a result of the small size. The size of these atoms play a major role in the properties or periodicity of this element. They play a major role in the property or the periodicity of this element. Okay, so like I said, the size play a very important role, and one of the reasons why we have this is because we just discovered that smaller atoms show a greater tendency to attract electrons because they are small, so they are closer to the nucleus. They show a greater tendency in attracting electrons, and that is why, because they have a greater tendency of attracting electrons, it shows that energy is released more as electrons are being added. Remember, we're talking about electron affinity, and nevertheless there's still a discrepancy on this. A major one I will just quickly run through in the aspect in period 2, where we have beryllium, and we have beryllium, and we also have nitrogen in period 2. Yes, beryllium and nitrogen in period 2. Now, these two, they are known to have a very different disorderliness when it comes to the electron affinity, and this is responsible as a result of what we said earlier. Beryllium has an electronic configuration of 1s2, 2s2. This is a closed shell, and this makes it to act as if it is inert and doesn't need more electrons. And because it doesn't need more electrons, because electrons cannot be added to it, there is no need for energy to be released, and that is why the value of beryllium is quite seen to be a disorder then, or an anomaly. The same thing for nitrogen. Nitrogen has partially filled 2p3 already, so that means it is half filled, and it doesn't need, it is more stable at this point than when an incoming electron comes. But there is something I would like to note in the area of electron affinity. We have some elements that actually have first electron affinity and second electron affinity. For second electron affinity, we have something of this sort. Now, it is discovered over time that the first electron affinity of an atom is negative, but the second one is positive. How is this possible? Because the incoming electron coming into, after one has been added, another one is coming into it. There is a repulsion. They tend to repel each other, thereby requiring energy for you to put them together. Let me come that again. Let me come again with that. So there's an electron that has been added. Another electron needs to be added. They are very much repelling each other because they are negative and negative. But for you to stick it and make sure it's add, you need to add energy to it. And when energy is being added to something, it becomes endothermic, which is responsible for making it positive. This situation we have in the case of oxygen, where we realize that there is an increase in the second electron affinity. There is an increase in the second electron affinity. The first one is known to have -142 kilojoules per mole, and the second one is known to have a higher value as a result of what? In fact, it's known to have a positive value. Is known to have a positive value, and this positive value is plus 844 kilojoules per mole, and the overall reaction is known to be about 700 kilojoules per mole. I would have written the equation, but time is not on our side. So the next one we'll be going to is the last aspect, which is known as the electronegativity. Electronegativity. Electronegativity is known as the measure or the tendency or the ability for an atom to attract electron to itself. If we have been following from the other periodicity, you realize that at this point we have just less work to do, because at this point you realize that electronegativity, the trend for electronegativity is that it increases across the period and decreases down the group. Electronegativity increases across the period and decreases down the group. How is this possible? From the definition, we said electronegativity is the tendency, the measure, the ability for an atom to attract electron to itself. So, like I said earlier in the aspect of electron affinity, I said that smaller or small atoms have the tendency to attract electrons than larger atoms. Because why? They are closer to the nucleus. So there tends to be a pull that comes from the nucleus. So now, this is what we experience in the area of electronegativity. So electronegativity is, and you know, across the period, we said atomic size, what? It reduces. So if the size reduces, that means they become smaller in a way. And because they become smaller, that means there is tendency for them to attract electrons more as you move across the period than you move down the group. And that is why there are three most electronegative elements which are known to be small, and those the most electronegative elements are fluorine, oxygen, and nitrogen. Fluorine, oxygen, and nitrogen. I call them fun just to play with them, or NOF, whichever one you like. So fluorine, oxygen, and nitrogen, with fluorine as the most electronegative. So that is art on the periodicity of elements. I hope you enjoyed this lesson. I hope you enjoyed this lecture. Please do well to share and subscribe to our YouTube channel. And if you want to reach us on our phone, we the phone number is +234 80 95990. You could chat us on WhatsApp, Telegram, or you could give us a call. Don't forget, again, this is Further Solutions Academy. Please do well to share and subscribe. Next class, we'll be talking more on an aspect of inorganic chemistry, or physical chemistry, perhaps physical chemistry that talks about chemical equilibrium. And please do well to check our YouTube page and follow us. You can leave a comment or contribution as you like. So we will be exploring the aspect of chemical equilibrium in our next video. Please do well to check next time. See you.